Okay, good afternoon, everyone. Thanks for coming. So the purpose of this talk is actually to introduce you a problem which I think is clean. And it is related to quantum computation, in particular quantum query complexity. So the main talk will actually be about the background and motivation. And in the end, I'll tell you the problem. So first, what is query complexity in the title? Suppose that we have a very large database of 0 and 1s, and we want to compute some Boolean function on this database. The issue is that it is too expensive to read the entire database, so we want to just probe a few locations and to know the value of f. So informally, query complexity is just the minimum number of queries that we need to know the value of f. Classically, deterministic query algorithm will be defined formally by a decision tree. So for example, in this picture, it describes an algorithm. In the beginning, it will query the first bit. And depending on the value of the first bit, it will either query the second bit or the third bit. So depending on whether it's a 1 or 0. So let's just say x1 is 0, and we will query x3 in the next. And we will repeat this procedure until we reach some leaf in this tree. And the label on this leaf should be the output of this tree. And we say that our tree computes some function f if the output of tree is always the value of the function f. Okay. And the deterministic query complexity of function f is just the minimum depth of tree that computes f. So the depth of tree is the longest root to leaf pass, the number of edges in the longest root to leaf pass. So like the number of variables you queried. Okay, so for example, we can look at this logic OR function, and outputs 1 as long as there is an input that is a 1. And this function has the maximum deterministic query complexity. You have to query all the inputs, because if your input is this 0 string, then you have to read every bit to know that there's no 1 in it. So that is a classical deterministic query complexity. And now let's move on to the quantum query complexity. So the feature of quantum mechanics is that of quantum parallelism. A cat can be both alive and dead at the same time. A bit can be 0 and 1 in the same time. And we will use unit vector in the Euclidean space to describe a quantum state. So in particular, if we want to describe one quantum bit, we can use the unit vectors. For example, 1, 0, 0, 1, the standard basis of this space C2. And we can also use vectors of the linear combination. So the standard basis will be used to represent the classical state of a bit, 0 and 1, respectively. And their linear combination will be used to represent the superpositions of 0 and 1. So this bit is 0 and 1 at the same time. So in general, we have a unit vector, which is of form alpha naught 0 cat plus alpha 1 cat. So some linear combination of the basis of the classical states of 0 and 1. And it has this interpretation. If you look at your quantum bit, you will observe I with probability alpha I of the absolute value of alpha I squared. So that's why we use unit vector to model a quantum state. And if we have a system consists of m quantum bits, then we were represented by a unit vector in this space C2 raised to the tensor power of n. So this is a space of dimension 2 to the n. And now you can imagine there is this set of orthogonal bases of size 2 to the n in a 1-1 correspondence between the classical states of n bits. So all possible 2 to the n combinations of the n bits. Any questions? Okay. So now a general quantum state would just be in this superposition of the classical states of n bits. Okay. Okay. Now in a quantum algorithm, we can define a query to be the following unitary operator. So we will have some quantum bits, and the first few quantum bits will be used to indicate the location that we want to query. So the query index. And the other quantum bits were used for computation purpose, which you can ignore. And when we make a query in the ith location, we will get xi, and it will be put into the amplitude. It will be put in front of the state. And in general, we can have the state which put the query indices in superposition. And therefore, in a single query, we will be able to access all xi. So this is like how we take advantage of quantum parallelism in a quantum algorithm. Okay. And now in a quantum algorithm, we can do other computations based other than a query. And a quantum computation can be described by a unitary matrix. So we can apply an arbitrary unitary matrix to our quantum bits. Okay, so now a quantum query algorithm will consist of like applying sequence of computations followed by a query. So we try to collect some information of the inputs, and followed by more computations, and then we can do another query, and so on. And initially, our state will be set so that all the quantum bits are 0 in the beginning. Okay. So now to output, what happens is we just measure the first quantum bit. And mathematically, what we do is we take our state and we project it into the subspace spanned by the vectors whose first quantum bit is a 1. So that is the probability that we output a 1. Or you can also write it as the sum of some amplitudes corresponding to those whose first quantum bit is a 1. Okay. Okay. Now we say that our quantum algorithm computes a function f if it outputs the correct value with probability at least 2/3. So quantum computation is probabilistic in nature, and we will allow some error here. And 1/3 is somewhat arbitrary. You can pick other constant you like. So that is quantum query algorithm. And the quantum query complexity of function f is just the minimum number of the query operators you need to compute a function f. Okay, so we will make some observation here. Note that the amplitudes here, if we view them as functions on the input x, then they're actually polynomials of degree at most t. Let me explain. So in the beginning, you have a vector whose coordinates are all constant. And then when you apply a unitary operator, you're just taking some linear combination of those coordinates, it won't increase the degree. And when you apply a query operator, so if you remember, what you do is you put like -1 to the xi in front of each coordinate. And that you can also think of as 1 minus 2xi. So you actually multiplied a linear function into each coordinate. So that will increase the degree by 1. And when you use t queries, the degree is at most t. Okay. And analogously, you can see that if you only look at the real part of your amplitude or the imaginary part of the amplitude, they are now real polynomials of degree at most t. And as we see that the probability that our quantum algorithm outputs a 1 is like sum of the real parts and the sum of squares of the real parts and imaginary parts of some amplitudes. Therefore, it gives you a real polynomial degree at most 2. Yes, okay. Okay, so all the discussions so far motivates the following definition: approximate degree. So for any Boolean function f, we define its approximate degree to be the minimum degree of a real polynomial, such that it approximates our function f pointwisely. So for the difference between the real polynomial p and f is at most 1/3 on any input on the Boolean cube.
You don't restrict P to a certain class of polynomials?
Real polynomials. P is a real polynomial. The minimum over all real polynomials. Okay. Okay, and we can now actually summarize all what we discussed so far by the following theorem. So we know that a quantum paradoxon will give you a polynomial that approximates your function f. So 2 times the quantum query complexity of a function is at least the approximate degree of the function f. So now you can actually forget all the things that we discussed so far. And what the message that I want to say is that by analyzing.
That's an inequality. It's not really the same size, right?
No.
So that's the answer to his question. Yeah. There's a lower bound.
Yeah, it is a lower bound. Yes. So the message is that by analyzing this analytical measurement, you can show limitations of quantum computation. Okay. Let's again look at the example of logical OR function. So the theorem says that the approximate degree of the logical OR function is at least square root of n times some constant, some absolute constant. And we have like matching upper bound. So we have quantum algorithms that use square root of n queries, and we actually can construct a polynomial of this degree. But let me just let's just focus on the lower bound side. And this can be actually proved. This is actually a straightforward application of Markov brothers inequality. Let me state inequality here. So for any real polynomial of degree d, then its derivative within this small interval cannot be too large. In particular, it's bounded about by the degree square times the supermon of the value of our polynomial within this interval. And why this inequality will imply the approximate degree lower bound of the OR function. So the OR function is a highly symmetric function. We can actually just look at its symmetrized version. So the univariate OR function. This function has domain 0, 1, to n, and it outputs 0 only if the input is a 0. So basically, it means that the input equals 0 means that in the input string there's no 1. Yes. So otherwise, there's 1 in your input. There are 2 in your input. There are 3 in the input, but they always output 1. So this is like the simultaneous version of your OR function. Now, for any polynomial that approximate your OR function, notice that in this part, there will be some point whose derivative is very large. So that's why the approximate degree of OR function is at square root of n. Okay, so this is one way to prove approximate degree lower bound. And another method to prove approximate degree lower bound that I want to mention very quickly is the following. So if approximate degree of function f is large, then we will be able to find a witness function. So in particular, this witness function will have high correlation with our function f. So take the inner product, then it must be large. And the second, this witness function will be orthogonal to all the low degree polynomials. So you can actually construct a witness function for the OR function, and you can also show that the approximate degree is at least square root of n. So these are the techniques that I want to mention. Okay, so now let me move on to the problem that I want to tell you. The triangle detection problem. So give you a graph of n vertices. Just the question is just if there is a triangle, and the triangle is 3 vertices adjacent to each other. And in this picture, there's no triangle. Okay, so the Boolean function will output 1 when there is a triangle, and these variables were used to indicate whether the 2 vertex I and j are adjacent or not. If it is 1, if they are adjacent, and 0 otherwise. Okay, so this defines a Boolean function. Okay, and the problem is just to determine the approximate degree of this Boolean function. Okay, so this is a problem I want to tell you, and let me tell you what we know about its approximate degree. So first, we know that the approximate degree is linear on the number of vertices, at least lower bounded by n, the number of vertices. This is actually a trivial lower bound, and because if you think about it for a little bit, you will realize that the OR function is actually a subfunction of the triangle detection problem. Yes. And this is the only thing we know. The upper bound follows from a highly non-trivial quantum argument, which is n to like 1.25. Okay, so that's all we know about this problem. Thank you.
Any questions?
I have a question. Can you go back one slide? Maybe another slide. Basically, this universal constant, yeah, how does that depend on the 1/3 that you picked?
Sorry, can you say it again?
You know, you have this 1/3 in your approximation definition.
Yes.
How does that relate to this universal constant?
Yes. So that this 1/3 means that this approximating polynomial, will be along this range.
Right.
Yes. So then that's how you can argue that the largest derivative is how much. So that would depend on this parameter.
Right. So how does it blow up? I mean, it gets the estimate. I mean, if I want a very close approximation.
I see. So I mean, it will depend on the error parameter, but we don't care about constant terms.
Okay. I'm just curious.
Yeah.
Examples where the speed up for a quantum is more than square root.
Yes, there are examples. So actually, so currently the largest speed up is cubic.
For which problem?
This problem is called the how to say this? It's called the k-fold correlation. So that has to go through a few steps. So first you will come up. I don't know how can I explain it.
Yeah, I just want to know. So they are the Grover is square root. This is square root.
Yes.
So you can get
Exactly. Yes. Yes. Yes, we can definitely discuss it offline. I mean, because that cubic separation is actually our work.
okay.
Yes.
There are no other questions. Let's thank the speaker.